This is Gastler, and in this video we're going to talk about falling objects. At the end of this lesson, you should be able to define free fall and explain how most things are not really falling in free fall, and explain why mass doesn't really matter and what does it mean for an object to be falling at terminal velocity. So let's get started. We're going to start over here. I'm going to zoom in just a little bit. So when we say free fall, we're talking about an object that is falling when it's under only the influence of gravity. Okay, that means that it has only gravity acting on it. So if we were to draw a force diagram, it would have one arrow, and that would be gravity. Anything that's in free fall has the same acceleration. All things, it doesn't matter how big or small it is or what shape it is, it's all the same acceleration. How is that even possible? Well, let's look at Newton's second law. Okay, so remember, Newton's second law says that A equals F net over M in an equation. And since it's only got gravity acting on it, the net force is the force of gravity. So I've replaced it with Fg. Now, we learned in, lesson 2 of this unit that the force of gravity is m times g, right? Do you remember that one? And you see how we have an m on top and an m on bottom? That means that, whoops, I've erased too much there. That means that we can cross out those two m's, and so that acceleration is actually just g, which is that, we called it the gravitational field strength before, and now we're going to call it something else as well, but that's at 9.8. This time we call it meters per second squared as the unit instead of newtons per kilogram. That's its value on Earth. It has a different value on other places, but that's okay. That's about 10 meters per second squared. That's an easier number to work with, though, so we can call it 10 meters per second squared sometimes. We also call g acceleration due to gravity. That's another name for it. We talked about that in lesson 2 as well. But not everything is in free fall because not everything is only acted on by gravity. There's that pesky thing called air resistance, and that reduces the acceleration. It keeps you from speeding up as fast as you possibly could. What that means is eventually things stop speeding up. They stop accelerating. That doesn't mean they stop falling. There we go. That just means they stop accelerating, okay? They're still falling. They're just not falling as fast as they were to begin with. That means they reach their terminal velocity. And terminal velocity is that maximum speed at which they fall. So let's take a look at it. We've got an example here. You can see these pictures that are on your paper. There's a guy jumping from a helicopter, and then he's falling, and then he opens up a parachute, and then the parachute is fully inflated. Not really inflated, but it's all the way opened up. He's probably falling a bit slower than when he fell out of the helicopter. So this guy's name is Bronco. He has a mass of 100 kilograms. He is not in free fall. That's because he's falling through the air. If he were in free fall, he would probably die because he needs air to breathe, right? So what we're going to do is we're going to look at Newton's second law as he falls down. But we've got a couple of extra forces here. So we've got air resistance, which it marks with an R. So in every picture, you've got Bruno. Let me circle it for you. You've got Bruno, you've got an R and a W in each of these pictures, okay? So we're going to look at each of those. And you've got a W for the weight. That's the force of gravity. So it's not just gravity on Bruno as he's falling. Well, it is at first because R is 0. And then we've got, when we think about it, we're going to look at the net force, which is the difference between those two because weight is down and the air resistance is up. So they're not pointing in the same direction, so we'll subtract them, okay? So again, our Newton's second law is that A equals F net over M. Okay, so in our first picture, we'll zoom in a bit. Our F net is 1,000 newtons because there is no air resistance, and its mass is 100 kilograms. 1,000 divided by 100 is 10 meters per second squared. So he is zooming down as fast as he possibly can. Well, he's not zooming down as fast as he can, but he's accelerating as much as he can. Okay. So he's going to be speeding up as quickly as he possibly can right when he leaves that airplane. But his body is going to feel some air resistance. So he's going to be experiencing some wind resistance. Right now it's picking up. As he goes faster, that air resistance picks up, which you might have noticed if you've ever stuck your arm out of a window while driving down the road. The faster the car goes, the more wind resistance there is. Now there's going to be 600 newtons because 1,000 minus 400 is 600 newtons of air resistance, but he still has the same mass. So now he has an acceleration of 6 meters per second squared. Now he's reached 1,000 newtons of air resistance and 1,000 newtons of weight. That means he has a net force of 0. Did he stop falling? No, he didn't stop falling. He just stopped accelerating. Here is where he has reached a terminal velocity. He's going as fast as he possibly can. Air resistance is preventing him from speeding up. He's going really stinking fast. He's just not speeding up anymore, okay? And then he opens his parachute. What happens when he opens his parachute? Well, he's probably going to feel like he's pulled upward, which is why this air resistance is actually bigger now than his weight. So we end up with a negative force. That just means he's being pulled upward. When he's pulled upward with this negative 200 newtons for his 100 kilograms, we get a negative 2 meters per second squared. That just means he's slowing down. He's still falling down. He's just slowing down while he does it, okay? And then down here, now that parachute is getting really open, okay? So he's slowing down a whole lot. That force pulling him up is really big. He's still going down. He's just being pulled up really hard. So he's slowing down a lot, okay? I don't know if you've ever ridden in an airplane, but you can feel that slowing down a lot. Slamming on the brakes, so to speak, okay? So he's slowing down a whole lot. That's what that negative there means. He's slowing down. He's not going up. He's never going up at any point in time. He's just slowing down a lot. Now we're back to that. Now that he's slowed down enough, that air resistance is a lot less. So he's got a zero net force now, and so his acceleration is now back down to zero. So he's not stopped again. He's still going. He's just going a lot slower, and he's reached another terminal velocity. His terminal velocity is a lot slower now because of that parachute that's open, okay? So that's what Bronco does. So that's what we're talking about with terminal velocity. Terminal velocity happens when I hope you can see these here. This little arrow right here and this little arrow right there, they're the same size, okay? So the air resistance and the gravitational force are the same size on these guys. All right, there's just one more thing that I forgot all about, but we need to add this in down here. So we need to talk about dropping objects while you're moving sideways. They did this in Mythbusters, and you've probably seen it before, but some questions are going to come up on the test, definitely. I don't remember if they're on the checkpoint or not. I think there are. When you're moving sideways while I erased a line, I didn't mean to. Just that one. There we go. Newton's first law applies to the object while it's moving sideways at a constant speed, and it's going to be dropping at the same time. And what that means for our object that's falling is that the sideways motion isn't affected by the downward motion. And so you end up with the object that is going, that's going to look really big. It's not, hang on. Erase that. Let's get a smaller dot. There we go. Okay, so our object going to the side might look like this, nice evenly spaced. Pretend those are in a straight line. And as it drops, it would go faster and faster. And as it is falling and going to the side, you see how it follows this like curved path. And so it's not going to stop going to the side just because you dropped it. Okay, when you drop it and you keep going, it doesn't land back over here. There were some questions about this in lesson 1. We were talking about Newton's first law, dropping things in the bus. They still land right where they were up with you because they were already moving to the side anyway. Okay, so there's some practice questions for you to ask. If you have any questions, make sure you ask your teacher. Thanks for watching.